In this presentation, we're going to take a look at how to solve a system of equations by graphing. Now, a system of equations is two or more equations that are on the same plane. So, at the top of the screen, I have a system of equations. My system of equations right up here is y equals 2x minus 3 and y equals x plus 1. Those are my two equations. And what I'm going to do is I'm going to graph those two equations on this x and y axis. Now, when I'm graphing those equations, I'm going to look for a solution. And a solution is a point that works with both of those equations. And my solution is going to be obvious to me on the graph paper if in fact my two lines intersect. So let's start by graphing y equals 2x minus 3. So I'm going to start by putting my y-intercept at negative 3, and then I'm going to go up 2 over 1, and up 2 over 1, and up 2 over 1. And you can tell I'm having a hard time plotting these points very carefully, but I'm going to go ahead and connect those points, and I get a relatively straight line. And now I'm going to graph the line y equals x plus 1. So this time I'm going to start at positive 1. I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. That's not so bad. I can see the point where those two lines intersect, and taking a look at where those lines intersect, it looks like that point is 4, 5. So let me just take a look over at the left here. So what happens if I plug in 4 for my x's and 5 for my y's? Well, in the top equation I get 5 equals 2 times 4, which is 8, minus 3. I do get 5 equals 5, that's correct. And then the bottom equation I get 5 equals 4 plus 1. 5 equals 5 is correct. So my solution absolutely is 4, 5. And I know that it's the correct solution because it's the point that worked in both of my equations. So let's try that process again. This time I'm starting with two equations, and my first equation, y equals 3x over 2 minus 4, looks like y is already by itself, so that's graph ready. Whereas my second equation, 2y plus 4x equals 6, y is not by itself, so I've got to isolate the y. So I'm going to subtract 4x from both sides. I'll get negative 4x plus 6. Now I'm going to divide by 2, and I'll get y equals negative 2x plus 3. So now I'm going to go ahead and graph those. I'm going to start with y equals 3x over 2 minus 4. I'm going to put my point at negative 4. Going to go up 3 over 2 and up 3 over 2. I'm going to connect those points with a straight line. Then I'm going to graph my other equation. I'm going to start this time at positive 3. So I'm starting at positive 3. Now I'm going to go down 2 over 1, down 2 over 1. I'll connect those points. And this works out really nicely. I have my coordinate at 2, negative 1. That looks like it's my solution. Going back and checking those, negative 1 equals negative 2 times 2 plus 3, that's negative 4 plus 3, that is negative 1 equals negative 1. Going back up to the top one, negative 1 equals 3 times 2 over 2 minus 4, that's also negative 1 equals 3 minus 4, that also checks out. So I know for sure that my solution to this problem is 2, negative 1. So now I just need to remember that there are certainly times where I might have a system of two equations that may not have a solution. For example, y equals 2x minus 3 and y equals 2x plus 6. So in this case, these two lines are parallel. I know that they're parallel because they share the same slope. They both have a slope of 2. So I just need to remember that this system has no solution. And I need to also remember that this system is called inconsistent. And then, of course, I do have this situation where I give you two equations that actually represent the same line. So it doesn't take much thinking to realize that that second equation is just double the first. If I were to get y by itself by dividing that second equation by 2, I would end up with the first equation. So these two lines are actually the same line. For that reason, I have an infinite number of solutions. My solution is any point on the line. And I would call this a consistent dependent system.